Products for our customers are stored in an area of 13,000 square meters. In this way, the Interfloat Group ensures maximum flexibility and continuous supply capability.
So good afternoon, everybody. We can start the session number 3 on metallization. My name is Olindo Isabel. I'm from Delft University of Technology. We have a lineup of 5 speakers for this session of today. And we start with Dr. Yu Yao, General Manager at Sunwell. Please take the stage. And she will talk about design for higher reliability and low carbon footprint, a case for silicon heterojunction solar cells and modules. The floor is yours.
Thank you for the kind introduction. Good afternoon. And it's my pleasure to be back to this heterojunction community at this difficult and challenging time of the industry. I think we have a friendly and open community here, which is very precious. I'm going to present our work at Sunwell done jointly with Tongwei Solar on the copper plating for heterojunction solar cells. So last year in the same workshop organized by Huasun, we were presenting that for a sustainable, non-limited manufacturing capacity of heterojunction, we need to achieve silver-free, indium-free, and bismuth-free schemes. And today we are able to say that we have a solution ready, industrial scale for silver-free. You can see from this Bloomberg survey that there are 5,500 tons of silver used by PV industry last year. And last year they were also claiming that for different technologies, this amount of silver is needed. And we see from last year till now, the industry has done a lot of work to reduce that. And nowadays, it's 9 to 10 milligram for TOPCon and 12 to 15 milligram a watt for heterojunction cells. These are in terms of paste. And we know that there are paste with reduced silver content, so we are doing better than the figures in the Bloomberg report. However, with low silver content metallization, it's typically like this silver-coated copper paste with the ball-shaped copper particles, 1 to 4 microns in diameter, 50 to 100 nanometer thick coating. And we know from actually the literature where putting a stack of silver and tin on top of a copper, both tin and copper will diffuse towards silver. And especially the copper diffuses through the grain boundary of the silver and leaves behind these voids. And actually the voids you can see in the literature, you can also see from like a commercial silver copper paste picture. So that means the copper have diffused outside the silver, and therefore in modules actually you need good protection using encapsulant with low water vapor transmission rate and low oxygen transmission rate. You have to protect the module from the edges, from the J-box, and for example, using this butyl sealant. And at Sunwell, we are developing high reliability, low carbon footprint technologies. For example, copper plating turnkey solution. This is a picture taken at our customer site. This T6, as Dr. Long already introduced this morning. We have also had some delivery of multi-gigawatt scale of TOPCon wet processing equipment. It's on customer side in production. For copper turnkey solution, we have developed some of the necessary materials, resists, chemical additives by ourselves. And we have also a small portion of our business as the BIPV tiles. This is, some of you might be familiar with the location, a picture I took in Neuchâtel a few days ago. And this is actually the building which I believe many of the people working for Rothenrau, Meyer Burger, CSEM, they have done their PhD in this building, and we are we are very lucky and we are proud to say now the roof of the building is 100% covered by Sunwell tiles. So going back to the copper plating turnkey solution for heterojunction cells, our process, we start with the seed layer on both sides. So we have developed the equipment, process, materials necessary for coating, firstly, the seed layer on both sides and doing light exposure to have the separation of where the openings should be, where the masks should be, and with a wet chemistry inline machine for making the openings, and also an edge protection equipment and material to protect the edges. And then we do the plating and finish with the resist removal, edge back, and surface finish. So for the pattern definition, actually we released the first lab version tool in 2021. It's based on laser direct imaging technique. So basically there's the DMD chip that flips on and off and defines where the openings should, where the pattern, where the mask area should be. So it's fast in implementing new metallization patterns. You can basically draw like a CAD and put it in the software. The chip will do the job. But it's limited with a printing speed up to 160 millimeter a second. And it's using laser, so it's 405 nanometer wavelength. And this year we have a production machine with a proximity exposure method. We have the exposure time less than 0.3 seconds. And we have 2 wavelengths available from the LED light source. And now the single track machine has a throughput more than 7,200 cells per hour. And this is a typical cross-section of the opening. And in terms of cost, you can see the big part of it is actually the resistant material itself. So the unit is in RMB cent a watt, so it's still low. For the edge protection, it's necessary to achieve good reliability because basically all the conductive surfaces in contact with electrolyte, if it's not meant to be your metallization patterned area, it should be protected. It also helps to keep moisture, metal, and other ions away from leaking into thin films and silicon substrates. So the edges and surfaces has to be protected. And our method is basically we have this dispensing wheel, and the liquid resist goes from the center, dispenses to the edges. The edge will never, the dispensing wheel, any part of that will never touch the wafer. It's only the resist material touching the wafer. And so basically the resist can be heat cured or UV cured. We have both types of resists available. And the viscosity can be in the range of 200 to 10,000 CPS. And this actually we found applications not only for heterojunction cell plating, but also for TOPCon, back contact, and perovskite. And for TOPCon, which is a bit of a surprise to us, it's actually when people were doing larger batch, when they have to involve the cassettes in transferring the wafers, they realized that in some cases, the edges of the TOPCon cells can clash with the cassettes, and that's where the exposed conductive surfaces can be. So actually, it's also necessary to protect the edges. And our method, you can see at the left, which is quite an extreme case because this wafer is laser scribed and snapped, so the edge is not regular at all, and we can still protect the edge without cracking the wafer. So plating for good reliability, in our point of view, 2 key questions. First is how to make good electrical contact to wafers. It needs to have a tight electrical contact to make sure that it's ohmic contact. But it also has to be soft in a sense that it doesn't damage the pyramids. So we presented also this last year that with a hard contact, like a small pins, even with 0.3 Newton of force, you will find some tips of the pyramids being damaged. And the risk there is usually these are the area where it has plated metal. So it's actually not active under electroluminescence or photoluminescence, so you are not going to see that there are metal covering the pyramids, but you might see problems during the reliability test. So that's one of the key problems we solved in our production line. And the second key question is how to make good copper diffusion barrier. And here we are lucky with heterojunction cell structure because we have the ITO itself, which is naturally a barrier, a good enough barrier. And in terms of the corrosion resistance, different TCOs also behave differently. As we said before, we should move towards a direction which is with reduced amount of indium or even indium-free. So this will be also our work in the future. And for plating, people also concerned about the water usage, wastewater treatment. We feel comfortable to say that the wastewater treatment, there's established methods, the cost is very controllable. However, we still want to try to minimize as much as possible the water usage. So we can put like an auxiliary equipment next to our production equipment to use this reverse osmosis system and to put the rinsed water back to the plating bath with concentration almost the same as the original electrolyte, so as to save also the copper source. So in terms of the cost effectiveness, there's an important question, which is the footprint of the plating equipment. With our method, we have done actually two options. One is with the horizontal plating and one is with the vertical. The vertical one with multi-lane, so you can assume that it's like multiple lane of cells but put vertically. And by our design and calculation to optimize the operation area, the maintenance area, actually it's more economic with a vertical design. And here the copper oxide powder is of course the driven cost part. However, with the plating technology, we can say it is not sensitive to the laydown of the metal at all. Therefore, whatever is the module interconnection technology, you can feel free to basically put zero bus bar, SMBB, this kind of design without worrying too much about how much metal, how much paste is used. So it's not sensitive. And going to the resist removal and etch back, so basically it's a polyacrylate resist, so it can be very easily removed just by diluted sodium hydroxide. And the copper seed layer we can fast etch by sulfuric acid with hydrogen peroxide. And we have developed an additive to improve the bath lifetime, as at the same time it's a stabilizer for the hydrogen peroxide, so we can reduce the consumption of hydrogen peroxide. And the tool we have on customer side is already running at more than 15,000 wafers per hour. And so now we are at a level where the efficiency today is 25.55, small scale, and this we have done by using almost full area ITO, and so the backside is not the standard pocket edge exclusion, and thereby we can increase actually the current to more than 40.4 milliamp per centimeter square. And we have also a clear roadmap to achieve more than 755 watt peak in production. And this will be translated to 24.4% module efficiency. So with that, I conclude the talk. So we did almost 3 years of joint development with Tongwei Solar. Now we are ready with a gigawatt scale plating line to deliver you heterojunction silver-free modules. The BOM cost, as I shown before, altogether, it's around euro 0.5 cent per watt peak at current level. And all the additives, in our point of view, has more cost down potential compared to other materials. And the module power, I have covered it. So, and the equipment, materials are separately available for any of you who might be interested in testing or to jointly develop a process according to your needs. And we will continue our work to develop reliable and low carbon footprint technologies. And with that, I thank you for your attention.
Thank you, Dr. Yao, for your presentation. Are there any questions, please?
Yeah, I have a question regarding that you had mentioned that you use a centrifugal process and you have a wheel. So I was just concerned whether the top edge and the bottom edge, are they the same in terms of application of the photoresist? So you use photoresist to apply on the edge, right? Yes. So now you are applying from the top, and the wheel and the wafer is rotating, right? And so my question is whether the edge, the top edge and the bottom edge, the thickness of the photoresist is same or different?
The top and the bottom thickness of the edge protection resist, that was your question. Actually, it can be tuned. We have like a slot, so the wafer goes like this. You can tune if it's upper half, lower half, how much is inserted inside. These are the parameters you can control to define the product.
Okay, got it. Thank you.
We have time for one quick question more. Maybe I have a question myself. Do you have a portfolio of different seed layers, or use the same seed for any type of solar cell, be them top cone or heterojunction?
For heterojunction, at the moment, it's copper seed. For the other cell structures, so we don't have vacuum tools. We are not in we don't offer the seed layer part, but we do know a few options. So, yes.
Thank you very much. So let's thank our speaker again. Next speaker is Dr. Jonas Huyeng from Fraunhofer ISE. He's head of the group Solar Cells, back-end process technology. And he will talk about reduced silver consumption for high efficiency and cost-effective silicon heterojunction cells and modules. Jonas, the floor is yours.
Thank you very much for the kind introduction, Olindo, and hello to everyone. I'm here today on behalf of Fraunhofer ISE, and as you can see, a long list of colleagues who have been involved in this work. Similar to the previous speaker, I would like to address the silver consumption for the heterojunction technology. But first, let me say that I'm very happy to be here because at Fraunhofer ISE we believe in collaboration, of course, with our academic partners and all the partners along the value chain. And let me also take the opportunity to thank our funding agencies from the European Union, the German Ministry on state and federal level. What we try to offer to the industry is, of course, joint technological developments in our PV tech from cell up to module level, and then, of course, testing and certification in the accredited laboratories. Talking about the PV tech baseline, we have been also developing the heterojunction, bringing it up to the same learning rate of 0.5% absolute in our laboratories, and here are some selected results. Let me take the opportunity to mention that all the equipment that we're using is coming from the collaboration with the European industry, so we have all European equipment in our processes. We are sharing the baseline infrastructure with the TOPCon baseline, except of course for the specific PCVD and PVD tools that we need for the heterojunction. We've been developing all these results for our own in-house processing, scaling up from M0 to M6, and there's also further explorations going on like thinner wafers or nanocrystalline silicon layers. We're also using the silicon heterojunction as a baseline for our bottom cell developments for perovskite and silicon tandems. I will show you shortly some results in the end. And yeah, we have also, of course, have some calibrated results on the bottom. So the first result here is a calibrated result on a gold chuck. All the other ones are on a black chuck, so there's a gain from the short circuit current. And then of course we also know we can optimize this with additional anti-reflective coatings to go beyond 24%. But we don't limit ourselves to only doing our own cell processing. We're also working with industrial materials, especially of course for the process development in the back end of line processing, so light soaking, edge passivation, or metallization, as is the topic of this presentation. So I don't think I need to introduce or motivate this very much, so let me just spend this one slide here. The numbers are depending on what source you take, but it's clear we have too much silver consumption with the current state of technology. There is some targets, I think these are like widely agreed upon now. This should be the targets that we need to approach. So 5 milligrams per watt, or then long term also 2 milligrams per watt is what we're aiming at. So first of all, the drop-in replacement for the current state-of-the-art silver technology, of course, you've heard it a lot already today, is silver-coated copper particles. So we did an extensive screening of different commercial opportunities that you can get from different manufacturers. I don't want to walk through all of them, just maybe some key findings from this. On the left-hand side, you can see the line resistivity on fingers on a logarithmic scale, and then you can see the left part is silver materials, the right part is silver-coated copper. There's a little detail here that they have been printed with different finger openings, and you can see that for most silver paste, it's pretty good printable for openings from 24 micron width. The silver copper particles, there's some materials that are not yet there in terms of printability, so they have an increased line resistance, but there's also some very good examples here that have pretty similar results in terms of that metric. And then you can convert this thinking about, because you're still using silver, how effectively are you using the silver to get resistivity reduction in your line width? And this is what this lambda ESU parameter is telling you. How much am I utilizing the silver that is in my material? And there you can see the prospect that silver copper pastes are giving you. You can increase, because you're already consuming the silver, how good you can utilize this by a factor of 2 or even more. If you want to know more details about this, I invite you to talk to me or check out our recent publication from my scientist Sebastian Pinger from the Metallization Interconnection Workshop, just published. And then I want to move on to showing some results on cell level. So here is an example where we've used an industrial solar cell precursor on M6 format, commercial screens, commercial paste, and we did this variation of the reference metallization with silver on front and rear side, only replacing the rear side silver with silver copper, or replacing both sides with silver copper. And you can see it in the same order from left to right: silver, silver, silver copper, silver copper, silver copper. And we had 0 busbar grid. The front side had 80 fingers, the rear side had 162 fingers, all printed with 25 micron opening. And then we did the IV measurement data with different bars. So we have a 5 busbar configuration in orange, a blue 9 busbar configuration, and then we used this also to estimate an 80 busbar situation. So what are the core findings here? We can see that there's a prominent drop in the JSC when we put the silver copper paste to the front side, because we have wider spreading of these pastes due to the printing, even if we're using the same screens. So they're not fully optimized, as I already said. Also, there's a higher laydown, so you can also see that the fill factor is increased because the line resistance for these fingers is lower. Of course, when you increase the number of busbars on your cell, this effect is less important. And then in terms of the silver reduction, we can then convert this all to the milligrams per watt. And while there's some challenges, or has been some challenges in the lab for these groups, we can already see that silver copper on both sides brings us halfway to the 5 milligrams per watt target that we have. And if we can optimize this further, going further into fine line printing with these materials, there's of course more potential to have. And then, of course, we would like to go the full way, replacing with fully copper material, at least testing where we are with this technology at the moment. So here's a similar experiment. We have a reference group with both sides silver, and then 2 different screen openings. So the first group has an 80 micron opening on the rear side, the other 25 micron. The front side is the same for all groups. And then you can see, if you look at the IV data, here only in terms of the efficiency, for simplicity, you can see that for silver, it doesn't really matter if you print it with 80 or 25 microns. This is already a really good optimized grid. But then if you look at the copper material that we had in this study, you can see that there's a challenge for the material to pass through the 25 micron opening. So again, there's a challenge in the printability that needs to be addressed. And then in terms of efficiency drops, we can see there's a slight efficiency drop for this wider grid lines and a larger for the smaller grid lines. It's not only the line resistance, we've also noticed that there's an increased contact resistivity for this material, so there needs to be some more work put into this. The good news, of course, while there's still room for optimization, is that the silver consumption, considering fully rear-side copper metallization, is already in the target range that we want to go to. So depending on what efficiency you're reaching, of course, the numbers change a little bit because you're changing the denominator, but you're already below 5 milligrams per watt. And then, of course, the next step of questions is, what about the reliability? So these are some quite fresh results. We haven't been able to do all the long-term testing, but at least the line resistivity that we've been monitoring for about a month now have been quite stable. So let me take 1-2 minutes to think about the module level and the silver consumption that we have on module level. Basically, there's different parts where silver can be consumed. Of course, there's the string interconnection, the cell interconnection, and typically you would want to do the string interconnection with a silver-free interconnection because it's not that important. But if you're having another solder here, then of course this can also contain silver. And then if you're going for ECA, of course the conductive particles are silver. We are leaving this out for another day of discussion. Here we want to focus on the low temperature soldering with tin bismuth silver alloy. And then if you sum all these wires up, and because people like putting up more wires on their cells, you can see that you're already entering in a range of 300 to 400 milligrams per M10 module. You can deduct about 10% if you are clever enough to do your string interconnection not with a silver-containing solder. But yeah, this is already some silver consumption that you have. How does it compare to the metallization part? Of course, the metallization part is still very dominating. This is a logarithmic scale, so there's a lot more in the busbar than finger metallization. Of course, again, depends on what type of technology or source you're looking at, but it's only one order of magnitude below, so if you're really decreasing the metallization, it makes sense also to consider this part of the consumption. Briefly showing how the cost breakdown on module level is. The very high cost breakdown part is in the material consumption. Here the wires are about 10% of the overall cost, so only the wires that we have there. The good thing is it's not yet only the coating that makes up this, but also the rest of the wires that is more complicated to make. And then I want to spend the next 2 minutes, as I said in the beginning, talking about perovskite silicon tandem, because it's the next generation, but it brings very similar problems. I have the feeling that at the moment people are more focused on other problems with this type of technology, stability. But yeah, there's also other things coming up. For example, the indium usage that we have in the TCOs. I think for now people are happy to use indium in their TCOs to getting to stable efficiencies, but it will be a challenge if you really want to scale up to terawatt production level. So together with a couple of partners, you can find them on the slide, and thank you all of you for the collaboration who were involved in this. We've built a little treasure map here, plotting the mobility and the electron density over a range of different experiments, and you can see in the color code what type of materials we've been investigating. So we're further trying to explore this, especially in this category, of course, for the terawatt PV compatible materials. So current state at our laboratories about the perovskite on silicon tandem cells, we're focusing on the hybrid route where we're using the same size of texture as we use for the industrial silicon heterogen junction cells. And with this, we had a recent result of breaching the 30% at 31.6% in efficiency. So this still is a small cell, so of course we want to scale this up. One step in this is the TCO. Here in the first part we have still the laboratory tool for small scale, and then we have now been able to get very good results also with the inline capable tool, and we'll continue working on these and other things. Yeah, that's basically what that says. One more brief glance about silver consumption. The problem will come up again, as I said, and we have another challenge to face because we have to go to even lower temperatures for the curing. So again, it makes sense to consider what type of materials are there and are they compatible with these lower temperatures that we need to maintain the perovskite. So here it's a smaller screening, it's only like 4 pastes, but you can see in the color code also the different curing conditions. And the good news is that there are already manufacturers producing materials that can work in a range of 100 to 130 degrees reasonably well. So this is something that we already have in our pocket. Of course, then we need to consider the silver consumption. So yeah, we will keep a look out on this and keep optimizing this also with all the learnings that we have from the heterojunction. And maybe one small cliffhanger here. This last group was done by dispensing, and I think there will be a talk later to explore more about this technology. With that being said, I'm at the end of my talk. I can briefly summarize. The silver copper gives a good opportunity to have a drop-in replacement for now that already helps us with scaling down to where we want to be. There's still room of improvement, at least from the snapshot of commercial opportunities that we've seen. Same thing goes for copper. It can be a very interesting option in the future, even more opportunity to optimize here. And then, of course, the long-term stability has to be demonstrated. There are further results that you can get from this, or further exploration of what this means on module level. I will not talk about this, but there's a brief snapshot here. Again, feel free to talk to me or check out this publication that are listed here. And then, yeah, for module level, I think it's still a little bit of time before we have to address the silver consumption in there, but it's not too far away. So thank you everyone for your attention, and I'm happy to take any questions.
Thank you for your presentation. I see already a question there.
Thanks. So you show regarding the silver copper nanoparticle, the silver that is covering the copper particles, let's say a span of the quantity of the silver content that goes from 25 to 60%. And you don't show, let's say, if you see some difference depending on the content of the silver. So instead, as I know, there's a quite difference. Let's say, can you comment on this?
Basically, it has the tendency, as you say, so the more you replace the silver in the material, the more you have to rely on the copper. It still depends on how you're making it and what other materials or how you're doing the mixture. There's a lot of know-how for the paste manufacturers, but there's a tendency when there's a limit of how well you can scale down with reducing the silver in there, yeah. There's more details in the publication, but today I wanted to give a broad overview. But yeah, please feel free to check that out.
Any other question? Maybe just one sentence, Jonas. Any long-term plan for also plating at Fraunhofer?
Yeah, I had the feeling I was invited to talk about the screen printing, but yeah, plating is, we have a whole group working on plating technology. We have a promising spin-off who are also here. Thibaut is in the back. So we have made some developments that are now ready to be commercialized, and yeah, I'm pretty sure Thibaut is happy to talk to anyone who wants to discuss these further.
Thank you very much. So let's thank our speaker again. So before I give the floor to the next speaker, very important announcement. We are almost at the end of the first day of the workshop. Please do not go away after ending this session, because Trisan has prepared a fantastic aperitivo. In Italian, it's happy hour. Yeah. So please don't go away. Stay with us until the end of this session, because then we are hosted by Trisan for a nice aperitivo. So the next speaker is Dr. Bertrand Pavier-Solomon, group leader at CSEM. He will talk about recent advances on copper electroplated industrial heterojunction solar cells and modules. So Bertrand, the floor is yours.
Thanks, Lindo, for the very kind introduction. Good afternoon, everyone. My great pleasure to be here today in this great venue to update you on our results on plated heterojunction at CSEM in Switzerland. So I will start directly with a brief recap of our process. So it's what we think a very lean process for plating heterojunction. It features only 3 steps. It starts with screen printing a very shallow seed grid, ideally made out of pure copper materials, on top of heterojunction precursors with thin TCO. And then in the second step, which is actually kind of a key process, we deposit over the entire wafer surface a dielectric masking layer. This layer has 2 purposes. First of all, it aims at combining with the thin TCO to provide a good anti-reflection coating. And secondly, which is actually the key for the selectivity afterwards, is that this masking layer will stay very tight on the TCO, but will feature some discontinuities on top of the paste particles, and will leverage on these peculiarities to conduct, in the third step, the overplating of the seed grid only at those locations. So with this approach, we demonstrated already some time ago some nice results. So just to illustrate, I'm sharing with you something we reported already several months ago. So it's the plating we realized on heterojunction precursors where the seed grid was deposited using pattern transfer printing. So just for the sake of the illustration, on the left you have the schematics of the PTP. So it consists in using a laser beam to transfer the paste onto the precursor. And as you can see on the SEM cross-section picture in the center, then we managed to obtain a pretty nice plated finger embedding this very nice copper seed grid. And the aspect ratio is pretty nice because we have an height of 22 micron with a width of 26. And we just, for the sake of illustration, I know we are here at the feet of Etna, but I hope you still excuse me if I take chance to make a bit of advertising for the Swiss mountains. A second advantage of our process is that it features pretty good adhesion with the POE foil. So to illustrate that, I'm comparing on this slide the peel force testing on different heterojunction cells. So we took first 2 commercial heterojunction devices. So they have standard ITO and standard screen-printed silver at the front. And for those, the peel force appeared to be pretty low, around 30 or 16 Newton per centimeter, whereas on the right, as you can see, when we submitted our plated devices to the same test, then there the peel force was found to be 5 times greater than what it is for the baseline devices. So we think it's also an important advantage in view of a future module stability. And maybe third point of general, let's say, comments. So, I mean, recently some people were challenging with me the reliability of the module with copper-plated devices. So I'd just like to maybe, let's say, recall that we have been in the past already demonstrating several good results with module stability with plated cells. So, I mean, long time ago, we already demonstrated glass-glass modules, either with solid ribbons or with matte wires, which passed several times the IOC norm testing. More recently, with the process I'm presenting today, we reached a full stability for TC and PTC for glass-glass modules with smart wire and with no edge sealant, with stability up to 2,000 hours of dampit, which for such, let's say, module scheme is quite remarkable. And eventually, if you want to have a bit more details, I encourage you to read this recent paper by my colleague Agatha Lachowicz, in which she is basically summarizing recent results of stability for plated devices in modules. So this being said, for today, I'd like to maybe focus on recent results we obtained on heterojunction precursors with thin ITO layers. And so let's get started. So for those tests, we relied on ALF M10 industrial precursors obtained from a manufacturer in which we are in collaboration. They feature 50 nanometer thick ITO on the front, and then we applied different seed grids on them. So we range from standard silver paste with standard on our openings. We tested obviously some silver coated copper paste and even advanced splits with pure copper paste on the back. So you can see on the picture that as received, of course the samples feature a typical brownish appearance because the ITO is too thin to perform a good anti-reflective coating. But then on the right, you can see that once we completed the devices with the masking layer plus the copper plating, then we fall back on a, let's say, much more standard blue color, which indicate that the RC is pretty good. Let's have a look now at how the line resistance is evolving on the as-received state versus after plating. So if you first look at group B, C, and D, so the one with either the standard silver paste and the SCCPs, well, you can see that, I mean, after plating, we have a twofold reduction of the line resistivity, which is very well expected. Maybe of interest on the results of the group E. So those one features at the back a pure copper paste, and as such, I mean, as received before plating, they feature a pretty high line resistance, which would limit the fill factor of devices made thereon to 40% roughly. But as you can see, once we do the overplating on those, then the line resistance fall back again to values very similar to what you could obtain with pure silver or SCCP paste. And I will actually come back to this point a bit later on. Here we have a couple of pictures on how the line looks like before and after plating. On the left, that's the seed grid. So here the cross-section is in between 100 to 200 micrometer square. And you can also notice that, across the line, there is this typical inhomogeneity of the height, which is a result of the printing process. And conversely, on the right, after plating, well, first of all, the cross-section is increased up to 400 micrometers square. And second effect is that, I mean, here the height is much more homogeneous across the finger due to the leveling effects provided by the plating process. Here are some cross sections of the lines after plating. So you can recognize on the picture on the left, the bulk part is the seed grid. In that case, it was made out of pure silver, but can be also made out of something else. And then it is tightly surrounded by the copper cladding here. Something interesting which we actually reported already in the past is that, as you can see on the right, we have the copper metal penetrating pretty tight into the seed grid, which is beneficial both for the mechanical stability of the contact and also for its electrical property. So let's dive now into the IV of those devices. So, and we start with the JSC on the top left graph. So again, so as received, those devices feature a lowish JSC because, I mean, the thin ITO is not a good RC. But then, as expected, once we completed them with the masking layer and the plating, then we fall back on JSC, which is perfectly on par with the reference featuring full ITO and full silver. Similarly, for the fill factor, I mean, as received, the grid resistance is too high to perform good, but then after plating, we again raise the fill factor to the value similar to the full ITO, full silver baseline. VOC-wise, I mean, one interesting point to mention is that we observe that already in the as-received state, there is a 1 to 2 millivolt VOC penalty for the thin ITO. We ascribe that to a non-optimal alignment of the band with those thin ITO. But what is interesting to notice is that this VOC difference is not made bigger after the plating, and sometimes is even actually partly compensated by the process. So overall, I mean, efficiency-wise, I mean, all those groups with plating perform very similar to the reference, which was, I recall again, a reference with a full ITO thickness and a full silver printing. We selected some of the best devices of those groups and sent them to ISFH for certification. And then the best one came to be a 24.6% device, which we were, of course, very pleased with. I promised to also give an explanation on this group E samples featuring pure copper paste on the back. So as I said, in the as-received states, I mean, they feature very low fill factor because this copper grid on the back is not suitable for good transport. But then, after plating, the fill factor is pushed much higher, so close to 78% in that case. So it's very encouraging. I have to say that those devices, in particularly, are plagued by, let's say, unexpectedly low VOC, which actually was the case already before the plating, and which somehow stems already from the processing stage because they were featuring, let's say, pretty poorish PL signals compared to the devices in the other batch. So globally, I mean, there should be room for improvement to have a pure copper approach with those devices. I mean, the previous speakers mentioned about the edges, and I'd like maybe here to insist that with our process, because the masking layer is also present on the edges, then we do not have any parasitic plating on the edges, and so those edges are very well protected by the process, which might also be an advantage in terms of future upscaling and mass production. We even went one step further into challenging the process with even thinner ITO. So in that case, we received half G12 heterojunction precursors with 30 nanometer only ITO at the front. And again, long story short, after plating, the efficiency was very similar to the reference with the full ITO thickness. The only caveat is that, surprisingly, the GSC was notably lower than the reference, but we turned out to identify that it was because this thin ITO was somehow peculiarly featuring a very high parasitic absorption, and so we're of course working on that with the customer to come back with a thin ITO featuring much more transparency. And in case you still have not enough with thin ITO, I encourage you to have a read at the poster of our colleagues from CA, Adeline Lantern, who actually applied our process to precursors with 15 nanometer thin ITO. And so you can access the poster online in the proceedings of the Metal Workshop. All right, then let's now conclude with the cost calculation of the process. So I'd like first to emphasize that, I mean, all the data we are using for those cost calculation, we received them from a multi-gigawatt Chinese manufacturer. So, I mean, they represent the current best practices there. So we are considering three scenarios. The first one is the baseline screen printing process, where we use 50% SCCP and full ITO thickness at the front and at the back. And we benchmarked it against two plating options. Option one with a 30% SCCP and a reduced thickness of ITO at the front and at the back. And the second option, a bit more aggressive, where we also replace the tissue at the back for an indium-free alternative. And here you go. So, I mean, let's say on the additional cost side for the plating, then obviously most of the costs are stemming from the fact that you have to add a tool for the masking layer and the plating tool, plus the chemicals and the gases to be supplied to those. But conversely, on the saving side, most of the savings are done through the reduction of the silver paste with the reduction in the tissue thickness coming, let's say, in a second order effect. And altogether, I mean, the process cost for our operating process was found to be lower than the reference. Of course, we expect this difference to be even greater once even more cheaper copper paste would be available on the market. And at the end of the day, what is interesting is that with the approach we propose, you can reduce the indium consumption below 1 milligram per watt peak at cell level, which is also very important for the future, let's say, upscaling of heterojunction as a main technology. So now it's time for conclusion. So I hope I convinced you that there are many advantages of our plating process. There are 6 of them I would just like to recap. So first of all, I mean, there is no need for additional treatment to protect the edge, and we have no ghost plating there. The round shape of our plated fingers is beneficial for dry trapping. We can save indium up to 70% and silver in a very appreciable amount. And last but not least, I mean, our process also proved to improve the adhesion between the encapsulant and the cell, which is good. And also involving masking layer might be beneficial also to mitigate the UV degradation of those devices. So with that, I'd like to acknowledge the funding agency and of course to thank you for your attention. Thank you very much.
Thank you, Bertrand, for your presentation. Are there any questions? So I do have a question. I think in your slide where you present your process, you deposit a dielectric layer after
Yes.
printing your seed. And that layer is done with the PCVD or?
So if I can I get back the slides somehow?
Can you put up the slides, please, again? It's coming.
Thank you very much. So yeah, thanks for the question, Olindo. So the question is regarding
for the ARC.
The deposition method for the masking layer. So, well, basically not secret, so we benchmark different methods. Most of the results I've presented today, they were obtained with PCVD deposition, but we also tested ALD, and it's working really well. So I would say you have still quite a bit of freedom to operate, to choose the best method according to your process and maybe also your design of the line.
My question was about, okay, if you have to use PCVD,
Yep.
Is it a process that I can imagine can introduce some contamination in your reactor? So you have to clean the reactor, or would you advise at industrial scale to have a reactor per se for this?
Yeah, rather the second option. So of course, we rather imagine to have a PCVD or an ALD tool, at the back end side of the process, because of course you don't want to use the same tool in which you are using for your intrinsic layer and so on.
But then the CapEx will change.
But it's taken into account.
Taken into account.
So,
Thank you. See you, Marcos. Thank you.
Welcome.
Do you feel a difference regarding the quality of the anti-reflection coating that you will have with the PACVD or the atomic layer deposition? So in one case, this means that you can have pinholes, and in the other case, you will not have pinholes, but this changes, as Livio was saying, the CapEx and so on.
Yeah, thanks, Marco, for the question. So, I would say now the favor is much more into the PCVD layer because, of course, depth rate is much higher, and so it combines much better with the thin tissue, let's say. But in principle, let's say, you could do it with the ALD, but of course, at the expenses probably of the process time. In terms of, let's say, selectivity, honestly, we did not notice any big differences. Of course, you have to tune each time the process, but you could do equally well plating with an ALD masking layer or with a PCVD one.
Okay, in view of time, let's thank the speaker again. Thank you, Bertrand. So our next speaker is Dr. Marco Ballucani, Chief Executive Officer at RISE Technology. Wait for the slides to see the official final title. So, Copper Industrial Route for Photovoltaics. So, Marco, the floor is yours.
Thanks for the introduction. Very pleasant to be here. And I will present, let's say, our vision in RISE Technology of which can be a copper industrial route for photovoltaic and offshore. Then we will try to convince you that ours is the best one. But so I'm presenting, let's say, the work is done by the three persons that you see down here. Let's say these are the three crazy guys that founded RISE Technology. So I will not read you let's say, the points that I will cover. So I will briefly introduce you who is RISE Technology, because I believe not everybody knows it. So we are a small and medium enterprise. We founded, let's say, more than 10 years ago. Let's say we were working on PV modules manufacturing, and now we're concentrating also on solar cell equipments. The production unit is in Padova, San Martino di Lupari, where we build all our equipment since then, 2021. We also have a space in Passo Martino, here behind in Catania, and an innovation hub, where we have all the facilities for 3D manufacturing, and then perhaps you will understand why. And the legal office is in Rome. Here you can see how many we are now, then we're growing. And let's say exactly the quarter 2004, we had an important investment. So the AEC, the European Innovation Council Fund, and CDP, the venture capital or the National Italian Fund, entered in our company, investing 3 million euro. So let's say exactly we come to the point of discussing the importance of copper, or which can be the route. So we see that, and everybody was speaking, we have to necessarily go down with the silver content, okay? But if you see, in any case, we are, and this is the prediction of the National Technology Roadmap, May 2024 was updated, and you can see we are going almost in 2034, and let's say on 7 milligram. So now they're showing this value, but let's say from an industrial point of view, it will take some time to reach it for sure. The problem that it's questioning, if you see, is in 2021, silver, let's say, respect the total market was only 11%. Today, in 2023, we're becoming 18%. So, and then if you see an historical trend of the price of silver, what happens is that if you try to put the slope of the increase in time and your decreasing quantity of silver at the end, your cost of silver will be more or less the same. That's the issue. If we don't decrease with a more, let's say, fast slope respect how is increasing the price. So let's say it's really a must to move to copper. And moreover, we will have a very low impact on the copper because the quantity of copper, the market share, is 3 orders of magnitude higher respect silver. The other reason also for moving to copper, this was made by Gatsbohr at CNS, it's also if we consider the environmental impact. So copper cuts you really a lot, more than 90%. And if you look, the last point, that one in yellow, you will see that that is also a high impact for the PV module. So it's very important if we move to copper, this will decrease quite a lot the environmental impact of the solar cell. So if we again take the silver, the international roadmap, they already show, they say, okay, we will use copper in some way. Everybody is speaking about silver that is covering copper nanoparticles and so on. So, but mainly the technology, if you see, will be screen printing, or the next one we will see another presentation, a variant of screen printing or something like that. But in any case, it's screen printing, nothing about plating or, except the first presentation, so something. But in any case, the prediction is that the market share of plating can be 6% in 2034, okay? So let me spend a few words on the silver-coated copper. That's why I was asking some question before. Because let's say you can see mainly they're working with a filling of silver with 20%, 30%, or 50%. Let's say we would like to have round balls because the coating is smooth and you have a low oil absorption. This means that you can fill quite a lot of material inside. If the coating, we don't want to have pores, we don't want that you have oxidation. But in real, and this was proved by ESA, consider that whatever you will deposit on top here, you will have oxygen passing through grain boundaries. And that's what it's called the red plaque. So what you will face, it's in time, depends how much time, but in any case, if you have oxygen and if you follow the equations, the chemical equation, you don't need water. So it's enough even only oxygen. You don't need to have a wet ambient. You will have some red plagues. You will have some oxidation. What this doesn't mean that it will not work. You will have an increase in resistivity. So that's why, if you take this nice paper, shows that in principle you have to use, and everything works well, if you keep the past within a 50% of silver quantity, okay? So if the quantity of silver that you're keeping inside your past is around 50%, and I'm seeing everybody, even applied material, is around 43 or 44%, if that's the average, the things work well. Moreover, you have to consider that for heterojunction, you're using not balls, but you're using flakes. So it's even more complicated than to cover it with silver. You can see here, you can have not a well covered, and there immediately oxygen will oxidize and make you a red plaque. So that's a, let's say, works well, but we have to see the reliability in time, okay, for the silver past. So if we give a look how we can bring copper to the photovoltaic. Copper past, exactly, I will recall the just previous Fraunhofer presented, they're working, they have some reliability, they say that they can work out, but we don't have still stability. Silver, okay, works, but in any case, it's not that if you decrease 50% of the quantity of silver, the price will go down. More or less, you will have a cut of 25% of the silver. So in any case, you are spending money, okay? So the other is copper plating. So what's going on copper plating? if we give a look to the International Technology Roadmap Photovoltaic in 2013, imagine they were giving a prediction that plating was almost covering 66% of the market and stencil printing only 33%. In 2024, they say copper plating forecasted perhaps 6% in 2034. So the question is, why? Why nobody is believing that plating will take up in the photovoltaic industry? Okay, so the story up to now. Plating started in 1805. There was Volta, Galvani, and then Brugnatelli in Pavia made the first gold plating using what? A tank. He put a tank, a salt of gold, took a piece and fully immersed it inside the tank and made the plating. Today, 2024, what we do. So how is the plating up to now? So the plating up to now, if you see, you're using bases, or you're touching the surfaces, or you're taking the wafer, you're putting it inside a tank. That's what you're doing. This is the first selective plating that I see, brush plating, okay? But in any case, you need some mask and so on. Let's give a look on the plating speed. 4 micron per minute, this is photovoltaic. For giving you an idea, we're speaking about 600 liter for 200 megawatt. The first presentation, Yao presented a machine you saw was 45 meter for 600 megawatt. Let's ask how many liter of chemistry they have to use. So the question is, you need a lot of solution, okay? So which are the issues? Of course, you don't have to put copper directly on silicon, but we know that TCO is a good mask layer. The question before, you don't have to have pinhole or scratches. So the layer that you put, if it's silicon, TCO, or whatever will be, you need, because you can have pinholes. Here you see, we have a technique for coloring. If the quality of the dielectric, of the quality of TCO is not good, you will have ghost plating, that's for sure. So that means that you have to protect your system. And then the other question is the speed of plating. Speed of plating means that you need at least 3,000 liters for 1 gigawatt of production. So imagine what does it mean. It has a machine that it's long 45, 50, 60 meters. So if you have to do 10 gigawatt, what you do? 30,000 liters or something like that. That's what it's, let's say, making big problems for. So if we go through the plating, let's say, or the different techniques, in any case, the wafer is fully immersed in a solution, okay? So difference of the step, you need to protect something. It can be a seed layer everywhere, like copper, we saw it before, or it can be a dielectric and so on. Then you have to do an opening, or before we were seeing lithography, seed layer, copper deposition, and then you can remove. So in any case, you are, let's say, consuming a lot of solution, and you're wetting all the wafers, so you need a protective mask that will cost and that will cover. So the idea is, can we remove the mask in some way? Can we reduce the quantity of liquids? And can we, let's say, have some Moses effect that is able to separate the water in somewhere and try to do something like this? So let's say having a confined liquid in some way, so we reduce the quantity of liquid that we need. We can make a seed layer, and when we deposit copper, copper will stay inside the liquid, will not go away because the liquid is there, okay? And this means that you are touching the surface only for 4%, imagine the fingers that you have, and then you need quite less quantity of liquid, okay? So that's how we try to do it. So we do what is called a dynamic liquid drop. We confine the liquid, and as soon, let's say, and this is the liquid that's changing, as soon as a surface will arrive, we form what we call a dynamic liquid meniscus, okay? And each one of these one is independent, so imagine, independently this liquid is like a damper, so he will adapt if you will have non-uniformities and so on, okay? So here is as we make it. This is our nozzle, and here you see the plating. This is coming out the liquid, the speed of the liquid, and here you see, because we touch the solar cell only in this point, here you can see, here we touch it, each dot is 50 micron, and the pitch, it's 100 micron between them. So the shape, then it depends even on the current density and so on, but let's say for heterojunction, in order to also, what we do is, the steps that we do, we do an heteroreduction, then we cover with nickel, and then we deposit copper. Here you see, for example, we are testing because this was micron holes that we realize, and then we touch the silicon only when we want. And this is the philosophy of the equipment, is that you change the mask like on a stencil printing, the nozzle that you need. You need to build M10, G12, or whatever you want. You change that mask and you can do the plating what you want. So what we measured is, do we damage when we do reduction of Ito the silicon? So we measured lifetime, and we don't have no kind of, let's say, impact on the passivation layer. What about the speed of plating? And here it comes. So if you consider the equation, and it was proved already times ago, so you have three terms that govern, let's say, the exchange of the ion. So mainly you can have, it depends on the gradient of the concentration, the potential, and then on the fluid speed, okay? So this is fluidodynamic. So depending on the speed of the liquid that you have, we are positioned more or less here, so we can go very fast. Remember, so we can do 1 micron per second, so this means in 10 seconds we put 10 micron, and that's squeezing down the dimension of the machine. And we have very nice quality of copper, the resistivity is very good, and here this means that we have very, let's say, also the, let's say, what is called, because we have less 200 orientation, so this means that even the high current density, let's say, will not have a migration of ions and so on. We measured the adhesion with this thing, and what we went to test is where we have the breaking. So the breaking mainly, if you see it, okay, here it's a shallow, but from this ADX analysis, you can see that we don't break the silicon. So, and we have an adhesion that is around 3 Newton per millimeter. And the nice thing is that because if you see, when we deposit the nickel, we are covering the indium balls, and then we do all the time like a simulation of the lamination process at 150 degree, and 150 degree, mainly what you are forming is an eutectic, okay? And this, it's very nice because it decreases the resistivity, and you see, we see a decrease after the let's say post-lamination of the specific contact resistance. And this is because we form the cylinder metallic, and that's the reason why then you have a really good adhesion. And also when you pull out, you still see Ito, but you find the nickel because you form the sinter metallic. So this is the machine that we are developing. We are building 2 of them. One, it will be operative the first quarter of 2025. And we're working with CNS, and then we'll be, after we test it and so on, we'll be delivered to them. And then there's this other one that it will be for 1,440 wafers per hour that will come at Trisan. So if I have to conclude, let's say we believe that this is the standard process. So we can do it, and we are introducing only one equipment, even better than silver, let's say, past, because you need to have a stencil, and then you need even to have an oven. Let's say with our technique, we do only plating directly, and that's it. That's the main advantage. We are working with 30 micron fingers, so that the equipment will come out with 30 micron fingers, and here you see the process. And the floor space, it's very low, and the quantity of liquid that we have to use is very low. This is the acknowledgements, and I finished. I even went over. Thanks.
Thank you very much, Marco, for your presentation. Are there any questions? I ask, can you comment on finishing your copper fingers for a future, I don't know, soldering or?
Let's say this technique allows you to put any kind of metal with this localized technique. So it can be even silver if you want. So depending on then what you have to do, if you want to use ECA, we can put 50 nanometer of silver in order to cover for giving the, let's say, the contact, because directly silver let's say silver passed directly on copper, I will never put it because you can have corrosion due even to the presence of the past. The other one is then, if we have to do soldering, for sure we will put nickel. It's a standard for semiconductor. And then you can put tin, and then you can go with a soldering technique. So you are free to do whatever you want in principle. Okay.
Thank you.
You're welcome.
I don't see any other questions, so thank you very much.
Excuse me, just a practical communication. Before we start with the aperitivo, we need to lock the room that we are going to use for luggage and clothes. So there is a small room here where someone of you put trolley, luggage, and clothes. Yeah, they must lock the room at 5:30. I mean, just after the last speaker. So before starting with the aperitivo, go there, take your stuff, and so we can make the hostess free to leave. Okay? Thank you so much.
Thank you, Antonio, for the information. So we go for our last speaker. So I would like to invite Dr. Maximilian Pospiskil. He's chairman, co-founder, and the chief technology officer of Highline Company. So welcome. And he will give us an update on the dispensing for heterojunction and more by Highline. So the floor is yours.
Thank you very much for the kind introduction. Good evening, everybody. I'll give you some update on our progress with dispensing. Let's start with the topic. You know this topic, mesh marks with screen printing. That's a general basic idea that we want to avoid by extruding a very small, fine homogeneous line on the solar cells. That's the basic idea. What came out of this, I will show you in this next 15 minutes. So Highline, as you see, the line is high, so that's why the name is Highline. We were founded 2019 as a spin-off from Fraunhofer ISE in Freiburg, and we have an exclusive contract for all the IP that we generated before, and now we want to enter the market. Started with a lot of product development, integration projects. We started up our production last year, and now we are at the moment of the market entry that is planned for next year. And to make it short, I have a video for you. I hope it works. And you can have a comment a little bit. So we do micro extrusion, as you see here. And we have our print heads. It's our core product with a single nozzle, and you will see later multi-nozzle. And we can do, of course, different shapes, all very homogeneous, with nozzle openings down to 10 microns. And very precise intermittent operation, which is very much the key, because, as you know, solar cells are single substrates and not roll to roll. We can do multiple steps, as you saw, and when you scale it, we invented this nozzle rails, and for an industrial product, you need to exchange those nozzle rails every now and then. And here you see applications, solar cell. This is our new application, hydrogen, flow field coating. This is full layer coating, and even on roll-to-roll processes it's possible. So how do we do this? We just exchange the bottom part of our printhead, and then with the new part you can do a different layout. And as we want to be flexible, it's not where we started with one nozzle and went to multi-nozzle. We started with multi-nozzles and went to one nozzle. That's something new, but the single nozzle is very attractive to some other applications besides PV. Yeah, so this, now you know, so fine lines, closed off system. So that's very important. the paste is not in contact with the ambient condition, and that's a very cool thing because you can add solvents or use solvents that are volatile. And this is a big difference to screen printing, because imagine you increase the speed of the lines. You also have to increase the length of your dryers. Then of course there's no contact anymore, no contact to the wafer. And if you have a contact with the wafer, there's a problem with the machine. So we do any parallel structures, and we can customize the nozzle kit depending on the application. So here again, our solutions. You see the M2 version in the middle, the G12 on the right-hand side, single nozzle on the left-hand side. And the single nozzle is actually very important to develop paste and processes on a small scale, because otherwise you can imagine you need to fill a lot of paste in those print heads, and they're quite heavy. You need a strong tool around it. And so we found with this topic you can really accelerate the development. And actually you can always demount the top part, the part in the front, the blue part, you can demount and put it in the freezer. This is very important for this community, because most of the paste you need to be frozen when stored. And so what we do is we just put the printhead in the freezer, and next day we defrost it and continue working. So we have the printheads, we have the nozzle kits that you can exchange and you can define the layout with. And then as there's a lot of screen printers around, we developed this upgrade kit, the cuckoo we said, because like the bird, you puts its eggs into a nest that's already existing, and which is the screen printer in this case. It's a very good tool to develop like this. We found there's a lot of applications in other markets than PV. For PV, this would mean that the speed of our process, which can be very high, is limited to this blade movement, like in screen printing. So in order to really roll out the full potential, it's better to have different automation solutions. So how do we control those parameters? It's not just like 3 or 4 parameters like in screen printing. We have a lot more options there. And we developed an AI-based inline process control and analysis system that keeps our process running. And we have really made great progress. Like I show you an example. When you start and there's something in the front, you need to open the valve and increase the speed at the same time. And then you end up with something like this, maybe in the first place. And then after 3 optimization steps, our AI controls it already like this. And in the end, even when, like, let's say, paste viscosity would change, or you have a stop of the line, there's no shear anymore, then you start over again. The AI can control all this, and it makes life much more relaxed for any operator. And in fact, we don't want to have too many operators on a line in a fab, right? So let's go to solar cells. So first thing, when you apply bus bars and fingers and you want to have different paste optimized for different situations, usually you do a dual print, and dual print in screen printing means there's a drying step in between. We are contactless, so we can, of course, do wet and wet printing, and that means you save 1 drying step. This makes your factory shorter, and your wallet stays a little bit more filled when you invest in new technologies there. And then, let's go to solar cells. So we do these fine line contacts, as I said, and we have a very strong partner here, Applied Materials, our friends here in Italy, in the north of Italy. And they set up a very, very cool machine that can handle all the automation. And we focus on our process, on our printhead. And what we achieved here, you see this here, our head lifetime. This is from Marco. He published this 2 weeks ago in Chambéry, and now we are at 1.5 million cycles already. The nozzle kit lifetime with this heterojunction silver paste here was 65,000 prints. Has to grow, of course, some more. And then the last thing, 5 minutes green-to-green kit change. This is a very important parameter for production. So we are happy to have this collaboration and making progress, and that's the way to really put this process from our facilities, very small, in Freiburg to the market. And then, what we also need is a paste. Now I'll show you how to do small lines with larger nozzles, or let's say smaller lines with larger particles that require larger nozzles. As he's shown by Katharina, who was a former PhD student at Fraunhofer ISE, the stretching of the paste works very well with dispensing. And the second thing is what we want to do with the paste is we need to qualify it, and for that we set up a little filter setup. We make sure that there's no buildup of a filter cake, because that ensures that we have a long lifetime of our components. And what we achieved here with this feature, you see here a 25 micron nozzle, but with some stretching agent added to a silver paste, we end up at like 7.5, or let's say shaded below 10 microns. The other thing is with copper, we haven't done this yet. We tried it. So what we see here is like a desired line width on the left-hand side, which is a potential. On the right-hand side, the desired material. And we are working hard on meeting those two sides here on the slide. So this is where we are very busy with. And yeah, let's show you some example of IV results. These are, I call it ancient M2 precursors. And they have no bus bars. And we compared screen printing with dispensing with the same paste, still silver, unfortunately, but it's silver. And what you see, we applied dispensing, and even though printing less milligrams, we had an increase on the JAC due to the small line width, VOC then same thing, and then better silver usage. We increase the fill factor, and then we have an increase in efficiency here. But then, where's the stretching? And stretching is the next one. Here, we made it even smaller. You see the further increase of the JAC. And you see we reduced the mass consumption from 28 to 19 milligrams and even surpassed all the other results. So it's really like you can really put this, the potential on the road when you work on the pace as well, not only on the technology. Yeah, and then there's the modules, of course. And you see on the right-hand side, and there's ECA. And ECA, there's several methods how you can apply it. I think here it's done with screen printing. And of course, we also do this with dispensing. And here we work together with our partner Mondragon. And we've already a few tools in construction. And so this is very promising. The results are very promising, and I'm happy next year to have this in the field. And with this, besides solar, which is, let's say, a little bit the insurance that we need these days, we also entered some other applications, and show you here some in the hydrogen world. So we have flow field coating here, and Maya coating potentially with our new full area coating application with our same printheads, just a little bit different kit. At the bottom, also high temperature solid oxide, electrolyzer cell and fuel cells. We achieved the solder dots for electronics and have some first revenues also in the automotive section. So with this, our portfolio is a little bit more stable, and I'm very happy about this. So summary, maybe the takeaways for today. So we have these printheads and nozzle kits in a very reliable state already, and we have the AI controlled process. So with this, we are ready for the market. And our key features, we have this fine line dispensing down to less than 20 microns. That's the goal. And we have also achieved intermittent coating, which is something very, very new. And we have a very strong partnership for integration in cell with Applied Materials and module with Mondragon. And I'm very, very happy about this. And working together with these professional companies that are long years in the market, and they know how it works in the industry, because that's something you learn as a startup, and sometimes you learn it the hard way. So we're ready for contactless high throughput manufacturing. And yeah, thank you for having the possibility to talk here. Thank you for your attention. Thank you for organizing this great event.
Thank you, Maximilian, for your presentation. Are there any questions?
Great presentation, Maximilian. One question, because you showed that you have a problem, or let's say you call it a little bit an issue, with the micronodes lifetime, that it's only 65,000 cycles. So if you compare it respect to stencil printing price, let's say screen, and lifetime, how you will compare your nozzle, let's say?
Yeah, it's a good question. Thank you. We have to match this price, so we aim on the same price per cell. Yeah, that's for sure. And screen printing is putting pressure on this on us. But generally, we don't have a wear in our components. It's about the paste. The paste has to run stable, and millions of cycles is also feasible.
The microphone. Volume.
Yes.
Thank you for your nice presentation. Maybe I lost some piece, but there's any limitation about metal material you can print, or you may dispense whatever you wish? I mean, use metal in electronic device.
Yeah. I mean, that's the thing with all these applications. There's a lot of applications where dispensing is known, and you find the metals, like the paste in the market that you can dispense. In PV, it's something, let's say, different in the metallization at least, and so there you need some slight adaptations. But we know how to do this, but it's also the topic where we need the most people for. Let's say it like that.
So just one question. So is the paste, is it the same paste, or you need to fine tune the viscosity for the dispensing application? So just I wanted to understand.
The results that I showed you is with the same paste.
Okay.
But when you really roll out the technology, it makes sense to have a different paste.
Okay. And so now this is for the, so even this can be applied for the TopCon and, for the back contact cells as well, using the same conventional, the commercial pastes as well?
Yeah, actually TopCon is a bit, let's say, easier because the particles are smaller. Like with this move to copper, the challenge is that the copper particles are much larger than the silver particles. In TopCon you don't have this, so you have very small particles. That's from the paste side, it's probably easier.
Okay, thank you. Thanks.
So I would like to conclude this session. We have had an excellent overview of technologies that are either already ready for the market or they are being optimized and being ready for the market with an excellent drive down of all the costs involved. So this is very interesting, I would say, takeaway from this session. Let's thank all the speakers again, and let's enjoy the aperitivo.
Yeah, just few words concerning this first day. Let me say that I really find all the presentation with such a high density of useful information concerning material processing, industrial scale, any kind, metallization, silicon, TCO. It was really more than I was expecting. So I'm really happy to be here. And again, thank you to everybody. I think also Mimmo would like to say something.
Okay, I agree with him. Of course, there were very high level of presentation, technology, and not only in terms of scientific work, but also for, let's say, transfer to manufacturing that is very important for us. So thank you for this day.
Oh, do not forget to take your luggage and coats, please, now before the aperitivo, so we can. See. You can follow the hostess, the ladies here.